Okay, so we are now into chapter 2, looking at atoms, molecules, and ions. And we're just going to breeze through kind of the beginning stuff here of the chapter around atomic theory and kind of its foundations. But atomic theory of matter really was first developed by John Dalton, the idea that matter could be broken into these small parts, building blocks that uh, make compounds. So, like the idea that water comes from individual compounds of hydrogen atoms and oxygen atoms, and John Dalton didn't necessarily know of or perceive of smaller items being electrons, neutrons, but really started the process of thinking about each element being made of extremely small particles and coining the word or using the word atom a little more commonly. So all atoms are given elements of a given element are identical to one another in mass and other properties, but the atoms of one element are different from the atoms of all other elements. So this really came out of kind of all the testing and laboratory work that had been done in the previous centuries, where people had started to isolate and discover individual compounds, and Dalton kind of took that background information and put it into his postulates. Next, atoms of an element are not changed into atoms of a different element by chemical reactions. Atoms are neither created nor destroyed in chemical reactions. And a variety of Dalton's postulates still remain true and have been expanded on. Some have been made false, but for the most part, several of his postulates are still true to this day. The next one being compounds are formed when atoms of more than one element combine. A given compound always has the same relative numbers and kind of atoms. So that's the idea that no matter wherever you get water molecules, whether it's in Washington State or in an urn that was stored in a Egyptian pyramid that's 5,000 years old, water molecules are still water molecules, still two hydrogen and one oxygen. All right. Now, the law of constant composition, so this is known as the law of definite proportions, the idea that elements come together in whole number ratios and to make up a compound. And then, of course, there's the law of conservation of mass, and this is the idea that the total mass of substances present at the end of a chemical process should be equal to the amount or the mass of substance that was present before the process. So your starting reactant masses have to equal your total product reactant masses. All right, when we start thinking beyond Dalton's idea of the atom being indivisible and the smallest thing, we start delving into the idea of there being even smaller particles that make up the atom. So subatomic particles, and the first one being the electron. And one of the ways to discover it was using a cathode ray tube, and creating a negatively charged particle discovered through the use of that, and you could actually determine its charge by putting a magnet near it, and you could bend the basically the emission of these electrons in that cathode ray tube. That was discovered by Thomson. And he measured the charge to mass ratio of the electron to be 1.76 times 10 to the 8th coulombs per gram. And I'm not too worried about you knowing that value at this point. We'll delve into that a bit more when we get into electrochemistry. But at this point, it's just noting the discovery of the electron and kind of its role in subatomic particles. Another component of understanding kind of charge and mass was basically trying to figure out, what is the mass of an electron? How can it be determined? So you had Millikan's oil drop experiment, where he basically had really fine spray of oil, and really, really fine, like literally at the atomic level or very small particles, and charging those and getting those to go through a very small kind of pinhole entry, so that and then using an X-ray um, to then view kind of the behavior of the electrons after they went through. And you can read a bit more about that in your textbook if you'd like. and it really determined the charge on the electron, or was another kind of piece that added to it. Another way to explore the atom was the discovery of radioactivity in substances that emitted radiation, because with that radiation, you're discovering a variety of pieces or things coming off it. So you've got Henry Becquerel, who was the first one to discover it. He made this famous X-ray of a hand with a ring on it. Um, and then Marie and Pierre Curie studied it. Unfortunately, many of the people that did early research into radioactivity died of cancer, which, you know, when you're working with radioactivity and have little understanding of the long-term impacts on health, it's bound to happen. Okay, so types of radiation that were discovered. So you have alpha particles, beta particles, and gamma rays. Alpha particles being large particles, very heavy, made up of what would be the equivalent of a helium nucleus, so 2 protons and 2 neutrons. Beta particles being radiation of, or something that's emitted the size of an electron. And then gamma rays. And with that, so you have different sizes, but also different charges of these items as they're being spewed out. So alpha particles being a positive charge, beta particles having a negative charge, and gamma rays having no charge at all, just being straight radiation. Okay, so then let's just briefly kind of buzz through kind of the structure of the atom and kind of what was thought to be the structure of the atom over time. So the first type, so around circa 1900, you had an atom where you knew that there was electrons, but the rest of it you didn't know. You knew that the atom was neutral, so therefore if you had negative electrons, then you have to have something positive. So they just kind of said, oh, you have this positive charged sphere that the electrons are kind of stuck in. So this plum pudding model style approach. And then next, when Ernest Rutherford shot alpha particles at a gold sheet, he scattered particles, and which uh, basically suggested to him that rather than the atom being just this big sphere of positive charge, there must be something very small but very dense in the middle that particles were not able to go through. And so the discovery of the nucleus, of there being some kind of very, very dense center to an atom, led to the addition of a nucleus in the structure with the electrons in the outside. And moving further, you know, the idea that most of the atom is empty space where the electrons kind of are around. Later on, protons were discovered, and then the neutron was discovered later on, even later in 1932. And if you think about it, electrons being negatively charged and not in the nucleus, easiest one to find. Protons, at least having a charge, made them somewhat detectable, or a little easier to detect, but neutrons being neutral, having no charge, being in the nucleus, made them much more challenging to discover. So now we've got these three subatomic particles, protons and electrons, both having charge, and then neutrons having having mass but no charge. And we get now a picture of what the nucleus is. So the mass of the electron, typically when we calculate molar mass or the mass of an atom, the electron has an insignificant or contributes an insignificant amount of mass to the overall mass of an atom. And so the protons and neutrons really are the pieces that add to the overall mass. So when we write symbols of elements, or when they're written, the way that we interpret them, so you write the symbol by its letter, and remember, first letter is capital, second letter is always lowercase. The bottom number is always going to be the atomic number, or the number of protons and electrons in a neutral atom, and that's also referred to as the Z number, atomic number. And then the mass number is always given above, and that's the combination of protons and neutrons that make up a neutral atom for that substance. So then you have a variety of what are called isotopes. Isotopes are atoms that have same number of protons but different masses, so therefore different number of neutrons that make up the nucleus. Some are stable, some are unstable. So in this example, carbon-12 is the most ubiquitous, or the one that you see the most, but carbon-14, being radioactive, is useful for archaeologists to carbon date recent sites, because it degrades over time because it's not stable. All right, another way when we look at trying to understand the molecular masses of things, or kind of the ratio of different isotopes, we use a mass spectrometer, where basically you fire the atoms down kind of a column, you put a charged entity on that, and you basically separate things out according to their mass. So heavier things are going to bend a certain way compared to lighter things, and so you can detect a variety of different masses of substances. So determine the different isotopes that are present. Because of this, the masses that are written on the periodic table are average masses of all the varying isotopes according to their percentage. So depending on what percent is, so you've got carbon-12, carbon-14, a very small percentage of carbon is carbon-14. And so if you look at, like, the average mass of carbon is 12.011, but and so therefore the large majority of carbon is carbon-12 type, but you do have carbon-11, carbon-13, carbon-14, but the majority of all the carbon on this planet is carbon-12. And average mass is calculated from the isotopes of an element weighted by their relative abundance. All right, so now when we talk about, so we've been talking about atoms, so then we organize these atoms into a periodic table, a way that gives us some order to how they are organized, how they behave. And so the periodic table originally was first organized by mass, but now we organize it by atomic number, because we now know there are protons, and so therefore it's a better approach to organizing these atoms. And then they are organized also by their patterns, the repeating patterns of behavior, how they react, how many electrons they lose, how many electrons they gain, what they bond with. All those behaviors determine how they're organized in the periodic table, or what we call periodicity. So when something repeats over time, so when you think of that first column, the alkali metals on the left-hand side, potassium and sodium, all those ones behave a certain way, very reactive in water, soft metal, and so to keep that behavior present and to make the periodic table a little more useful, we organize it the way that it is now. And so it's organized in rows, and which we call periods, and columns, which we call groups. Elements in the same group have similar chemical properties. This, again, should be reviewed from first-year chemistry. So some of the major groups that are known, or that are very common, would be the alkali metals, the alkaline earth metals, the chalcogens, and the halogens and noble gases. The alkali metals, alkaline earth metals, halogens, and noble gases should be common to you. The group 6A, probably less common, with the oxygen, sulfur, selenium, tellurium, polonium. But other ways that we organize, or where major groups are organized, so you've got your non-metals on the top right-hand corner, and then also hydrogen there over on the left. And then you've got your metalloids, which are kind of that in-between, where they have some behaviors like non-metals, some behaviors like metals, so they're kind of the transition. And having that little group memorized is really useful in being able to quickly decipher, oh, this is a non-metal, this is a metal, and that's a metalloid. And then the last group being the metals, which make up a majority of the periodic table, majority of the elements found on this planet, or really anywhere. It's not like you're going to suddenly have like a element that doesn't behave like these, but has the same number of protons. All right, and that's it. We will see you tomorrow.